So the last type of mechanical energy I'm going to talk about is called elastic potential energy. So when we have an elastic material, and we're most often going to be using the idea of springs, work is done in order to displace that elastic material, that spring, from its natural position. It both takes work to spread out or stretch out a spring or to compress that spring. And so when we do that, we are adding energy or potential energy to the spring. Now, there's all sorts of different kinds of elastic materials. We have rubber bands, you can have rubber balls, trampolines, all these sorts of things. But again, we will most often be dealing with the idea of a spring. So, in order to calculate the amount of work or the kinetic or the potential energy that that spring has, we use this equation, which is elastic potential energy is equal to 1/2 kx squared. Now, x is easy to define. That's the distance that you displace the spring from its original position. So whether you're compressing it by a certain distance or pulling it, stretching it out by a certain distance, that's what x is. Now, k has to do with the stiffness or the springiness of the spring, and it's called the spring constant. And the spring constant K is actually newtons per meter. It's how many newtons it takes, so what force it takes to stretch the spring by 1 meter. Okay, and that's just a property of the spring. It's a constant for that specific spring. So the stiffer the spring or the more difficult it is to compress or pull, the larger the spring constant, because it's going to take more force to stretch it a meter. So this right here is actually pictures of like a suspension in a car. Obviously that's going to have a really high spring constant. You want it to be very difficult to compress because the car weighs so much. Versus something like a slinky has a very low spring constant. It's very easy to stretch. Now, just like all the other examples, we can calculate the work by doing the change in elastic potential energy. And again, the property of the spring is not going to change, so the K is not going to change. So what actually is doing the changing is the X. So the change in the relative position will give you change in elastic potential energy or work. Now, I just want to mention again, we've talked about two potential energies, and there's lots of other type of potential energy, like chemical potential energy and thermal potential energy and electrical potential energy. And so any potential energy is typically given the generic letter U. So you might see it as U. Here, I like to represent and be a little bit more specific by putting EPE or GPE. All right, so let's do just a couple of examples. And then we are done talking about mechanical energies. So in this case, so here I have a spring, right? And it says that it requires 75 joules of work, or remember that would be 75 joules of elastic potential energy that I have stored in the spring, to compress a spring by some distance x. If it takes 110 newtons to compress the spring 1 meter, what is x? So in this case, what we have to recognize that our total energy or work is joules, 75 joules, and this 110 newtons in 1 meter, that's actually K. So that is the spring constant of the spring. So let's just pull up the Elmo really quick, and we can go ahead and I'm going to redraw the scenario here. So I've pushed it, I've applied a force, and so I've pushed and compressed the spring and made it smaller by some distance x. Whereas this would be like the natural position of the spring if I just let it sit there, right? Now, it would be the same idea if I were to pull in this direction and expand it out. But in this example, I'm using the idea of compressing it. So remember that EPE, or U for potential energy, is equal to 1/2 kx squared. So I want to find x. That was my question in the problem, and I said that I did 75 joules of work, or 75 joules of elastic potential energy stored, is equal to 1/2, and then it says it took 110 newtons to stretch it a meter. So that is what the K is, 110 newtons per meter. And then I just want to know what my x is. So in this case, to solve for x, I'm going to take 75, divided by 0.5 divided by 110, and then I would have to take the square root of that number in order to get x, and so I get that x is 1.17 meters. So x is 1.17 meters. Okay? So that is elastic potential energy.